Welcome to the TA Instruments QuickStart e-training course for the Discovery Hybrid Rheometer, also known as the DHR. I want to thank you for being a TA customer. Most likely you are a new user or have recently purchased a rheometer from TA Instruments, and we really appreciate your business. This is one of a series of recorded courses designed to ensure that our customers get the maximum benefit out of their TA Instruments equipment. This course is designed for new users of the DHR and the TRIO software used for instrument control and analysis. By the end of this course, our goal is to provide you with general operational knowledge and the confidence to work with the DHR instrument. If the DHR has not already been installed, please refer to the DHR Getting Started guide or contact TA Instruments service representative before proceeding. The course will cover the following topics: basic introduction to the DHR instrument, setup and operation of the DHR instrument hardware, introduction to the TRIO's control software, setting up the DHR for an experiment, and running an experiment. We will show two different experiments using two different materials. The first will be an oscillation frequency sweep measuring the viscoelastic properties of polydimethylsiloxane, and the other will be a flow ramp test measuring the viscosity of a silicon oil standard. We will conclude by pointing out some common features used to view and present data within TRIOs. Before we move on to discussing the DHR, a rheometer is an instrument that can measure both viscosity and viscoelasticity of a wide range of materials, including fluids, semi-solids, and solids. Viscosity is defined as a material's resistance to deformation. Viscoelasticity is a property of a material that exhibits both viscous and elastic character. A rheometer works by relating a material's property from how hard it's being pushed to how far it moves. It does this by commanding torque as stress and measuring angular displacement, strain. Alternatively, by commanding the angular displacement, strain, and then measuring the torque, stress. Let us start off by providing a basic introduction to the DHR instrument and highlight some of its hardware features. There are three different DHR models, all with very similar physical appearance, but with different specifications. Most likely your local TA Instruments technical representative has guided you to the model that would best fit your laboratory's applications. For reference, locate that model number on the front nameplate, as shown here. Each DHR is a two-component system. There is an instrument and a standalone electronics box. The electronics box contains the power supply and handles communication with the computer. The on-off switch for the unit is located on the back panel of the electronics box. The capacitive touchpad is used for some basic instrument operations. All of the controls available from the keypad can also be commanded from the control software. We will describe these operations in more detail as we go through this course. On the front of the DHR is a color display. The DHR model, serial number, and instrument's IP address used for computer connectivity are displayed on the top line. Below that you will find real-time signals, which are also displayed in the software control panel when connected to the instrument. Smart Swap technology makes it easy to switch between the different geometries and temperature control systems. The upper geometry has a magnetic band that can be read by the DHR. In turn, the geometry is identified and all relevant information required for operation is displayed in the software. The lower geometry is held in place through a magnetic coupling. Once plugged into the instrument, the DHR automatically recognizes the attached temperature system. In this section, we will cover some basic setup and operation procedures for the DHR. There are Getting Started guides available that discuss the basic setup and operation of the DHR and numerous accessories. These guides are installed with the TRIO software and can be accessed by double-clicking DHR AR Manuals icon on the computer desktop or via the Start menu. Additional instructional information can also be found in the TRIO software help menu, which we will discuss later. We assume the instrument is already turned on and has been installed by a TA Instruments service representative, but if your instrument is powered off, here's a simple acronym for you to remember how to properly power up your DHR instrument: ACP. Following the Getting Started guide, first make sure that air is connected and set to 30 psi. Remove the black cap or bearing lock from the draw rod and then turn on the power to the DHR. Again, step 1, make sure the DHR is connected to a clean and dry air source regulated at 30 psi or 2 bar. Please note, attempting to operate the instrument when air is not connected can damage the radial air bearings. Step 2. Remove the black cap or bearing lock from the draw rod. Hold the black cap with one hand and twist the draw rod counterclockwise to remove the cap. Step 3. Turn on the power to the DHR. The on-off power switch is located on the back panel of the electronics box. When the DHR has powered up correctly and is ready to use, the display screen status should read idle, and the keypad should have a green and red light on the start and stop buttons. Now that we've introduced the DHR instrument hardware and have it powered up, we can go ahead and start the Trios control and analysis software. The next few slides will display the basic layout and features of Trios software. All examples shown in this course were taken from Trios 3.2. The current release version of Trios software is available for download on our website. Once installed, open Trios software by double-clicking the icon located on the desktop or select from the Windows Start menu. The Instrument View window will open. Select the DHR instrument, and when the band around the instrument icon is green, press Connect. If an instrument-specific shortcut has already been created on your desktop, the Instrument View step may not be necessary. Once connected, the software will open and look like this, with the top ribbon and 3 vertical panels. On the left is the File Manager panel, and on the right is the Control panel. The center is the Working or Display panel. On the Experiment ribbon, there is a blue question mark icon named Help on the right-hand side. Browse the contents or utilize the search feature to locate in-depth instructional information regarding the DHR hardware and software. The file links used by the Help menu are in HTML format, which will open in the default web browser but do not require internet access for viewing. Access to all Getting Started guides can also be found through the Help menu. The File Manager panel has 4 different titled bars: Experiments, Results, Geometries, and Calibration. Trios will open by default in the Experiments view. It is in this window where all experimental parameters will be entered. Clicking down to the Results bar, this is where results are viewed and data analysis is performed. Currently running experiments will be displayed in real time, and data previously collected can be opened from this window. Notice some functional additions to the top ribbon have appeared. The ribbons in Trios are context sensitive, meaning there will always be an array of relevant options displayed based on the active selection. The Geometry bar displays a listing of all geometries entered into Trios. Geometry information and their calibrations can be accessed from this window. The Calibration bar is typically reserved for your service representative, but is used to access instrument calibration and advanced accessory settings information. On the right-hand side is a control panel. When connected to the instrument, this panel will be displayed by default. However, if not displayed, the control panel can be accessed by clicking on the Controls button from the top Experiment ribbon. In the control panel, the real-time values from the DHR are displayed, just like on the instrument display. Below that are several bars used to command specific instrument operations such as gap, environmental, motor, and axial force. Utilize the Help menu to become very familiar with these operations, as they are important for both instrument and sample loading procedures. We've covered some of the basic landscape in Trios and can now move on to setting up the DHR for an experiment. There are 4 basic steps for setting up an experiment. Select the temperature control system and install. Select and install a geometry. Set up the experimental parameters in Trios software, and lastly, load the sample and start the experiment. There are a wide range of temperature control system options available in the DHR, and there's a good chance you have at least one or more of these systems. For detailed instructions regarding operation, consult the corresponding Getting Started guide. For this course, we will be using the standard Peltier plate, but please keep in mind, the same basic operational principles apply for all temperature control systems. Before running an experiment, we must also select the best geometry for the measurement. This slide displays 4 classes of geometries and the typical range of materials that they are used to test. For this course, we will demonstrate procedures using a parallel plate. Once again, the same basic operational principles are also applicable for cone and plate geometries. Choosing the appropriate temperature control system and geometry is important to the success of any rheological experiment. For further information regarding geometry selection and other experimental considerations, we suggest the following resources. There is a brief TA Tech tip showing some various geometry options and their applications. There is also a 3-part pre-recorded series outlining strategies for better data in rheology. These videos, along with additional resources, are available from our website. Don't forget, TA Instruments provides a direct application support line where application scientists are available via phone or email. Contact information for application support will be made available at the conclusion of this course. For the first step, we have selected the standard Peltier plate as the temperature control system. We will now install the temperature system on the DHR, set the temperature, and allow time for thermal equilibration. The first step to install a SmartSwap temperature control system is to press the SmartSwap release button. When the light is solid green, the base magnet is no longer active. Now place the lower temperature control unit on the instrument stage with the directional tab facing forward. Note, the green light will remain on, indicating the magnet is deactivated for only 10 seconds, and it is advised to position the temperature control system within that time. Don't worry if the light goes out, just activate the SmartSwap release button again as necessary. If working with a Peltier-driven temperature control system, be sure to plug in the heatsink connections or the supply and return hoses because the Peltier elements require fluid circulation for proper operation. When using a Peltier-driven device, it is very important to have an external fluid circulator connected to the DHR. Make sure that the external circulator is turned on, confirm that all hoses and connections are clean and fluid level is full and flowing. When not in use, we strongly recommend to unplug the Peltier device and turn off the external fluid circulator. Next, plug in the SmartSwap cable and verify the green light has turned off. If blinking green, just press the SmartSwap button again until the light is solid green or turns off. Remember, the solid green light will only remain active for 10 seconds. Trios will automatically recognize the temperature control system. Confirm the temperature system connection within Trios under the environmental control panel. Here we connected the Peltier plate, so the display reads Peltier plate idle. Go ahead and set the temperature and press apply. Now the temperature control system has been installed and the temperature has been set. The second step is to install the upper geometry. Once installed, it's important to zero the geometry gap and, if necessary, calibrate the geometry. Before installing the selected geometry, check if the Geometry SmartSwap function in Trios is enabled or disabled. From the Experiment ribbon, under the Geometry menu, confirm the blue check mark where it states Toggle SmartSwap. If SmartSwap is disabled or not activated, click on the geometry icon and manually select the active geometry from the drop-down list. The active geometry will be indicated by a check mark. Prior to installing the geometry, press and hold the electronic headlock button until an audible beep is heard. Note that the rheometer head will rotate to its home position. The red light on the lock button will blink, indicating the head is now locked in the home position. Install the geometry, making sure to align the mark on the geometry shaft with that on the rheometer head. While holding the geometry, rotate the draw rod clockwise to tighten the geometry in place. If SmartSwap is enabled, Trios will automatically recognize the loaded geometry, but if deactivated, the geometry will have to be manually selected from the list. If the geometry does not exist in the current list, then a new geometry must be created. Follow the geometry wizard and save the geometry. For more information, a TA Tech Tip is available that discusses installing and calibrating DHR plate and cone geometries. Before zeroing the gap, it is recommended to lower the upper geometry to within 5 to 7 millimeters of the lower plate. There are two ways to raise and lower the DHR head, using the two arrows on the left-hand side of the touchpad or the two blue arrows within the gap control panel of Trios. Confirm the initial test temperature has been reached and the geometry is equilibrated. Then zero the geometry gap by using the button on the touchpad or the zero gap button located in the gap control panel. The DHR is now ready for use. Perform a geometry calibration as desired. At this point, the selected temperature control system and geometry have been installed and equilibrated at the initial test temperature. Now we're ready to walk through the basic steps of running an experiment. In this step, it is good practice to enter and confirm all parameters in the software prior to loading the sample. In this course, we will be setting up and running two basic experimental procedures. The first demonstration experiment will measure a viscoelastic sample, PDMS. The experimental parameters that will be used to measure the viscoelastic character and verify the crossover modulus and frequency are shown here. First, click on the experiment's view, then on the sample bar. Enter the information specific to the test, such as file name and file path, where the data will be saved. Next, click down to the geometry bar and confirm the active geometry. Verify the gap and trim gap offset settings. For PDMS, we will be using a 25 mm parallel plate with a 1000 micron or 1 mm measurement gap. The trim gap offset is typically 5 to 10% of the gap setting. Here we will use 5% or 50 micron trim gap offset. Also listed is a minimum sample required to fill the set gap. For reference, it is helpful to load approximately 10 to 20% access sample volume to allow for proper gap filling. Now click down to the Procedures bar. There are numerous procedures available within Trios, and the most common are displayed here. A single or multiple step procedure can be created using the options from the drop-down list. First, select the test mode, such as flow, oscillation, or step transient, and then choose the relevant test type. For example, amplitude sweep or frequency sweep as shown. For more information regarding experimental procedures within Trios, please refer to the Help menu. To test PDMS, select oscillation mode and frequency sweep test. Set the temperature to 30 degrees Celsius and soak time for 2 minutes. Make sure to check the box for wait for temperature, as this will command the temperature control system to first attain the set temperature before the soak time begins. Move down to test parameters and set the strain percent to 5%. Please note that this strain amplitude was confirmed to be within the linear viscoelastic region of PDMS under the frequency range selected. Choose a logarithmic sweep of angular frequency between 1 and 100 radians per second, collecting 5 points per decade. All settings below this point will remain at their default values. The experimental parameters are all set. Now we will load and trim the sample and then start the experiment. Please note to clean and dry both geometry surfaces before testing. Confirm that the temperature has been equilibrated to 30 degrees and the geometry gap has been zeroed at the test temperature. Take a small portion of PDMS and make sure there are no trapped air bubbles. Use an excess amount of sample to ensure the gap is filled completely. Go to the trim gap by using the touchpad or the gap control panel within Trios. Wait for the gap to reach the trim gap as indicated by the blinking green light on the touchpad and simultaneously monitor the axial force applied to the sample from the display or from the control panel. Don't trim the sample until the axial force value has reached a minimum, which is typically below 0.1 newtons or 10 grams. For PDMS, the axial force will relax in just a few seconds. Before trimming the sample, it is advised to lock the rheometer head using the electronic headlock button. This will prevent the geometry from freely rotating while trimming. After PDMS sample has relaxed at the set trim gap, trim the sample with a straight edge tool, and when finished, press the gap button again, or use the geometry gap button in the gap control panel to go to that final gap. A solid green light on the touchpad will indicate the geometry has reached the set gap. Again, be sure to wait for axial force to fully relax before starting the experiment. When using plate and cone geometries, be certain to verify the sample loading and inspect the sample edge. Improper gap filling or trimming can lead to erroneous results, which are difficult to troubleshoot from the resultant data collected. Be sure to also monitor the sample for trapped air bubbles, evaporation, or material leaving the gap during testing. Now that the sample is loaded and the test parameters are set, we can start the test. Use the Start button from the touchpad or from the Trios Experiment ribbon to begin the testing. Once the experiment has started, Trios will open the results view and the real-time data plot will be displayed. Here the PDMS frequency sweep results plot storage and loss moduli and complex viscosity as a function of angular frequency in radians per second. To view the experimental parameters or tabulated data, just click on the corresponding tabs at the bottom of the screen. Shown here is a spreadsheet view where you can review the data in tabular form and copy or export it to other programs. And here are the experimental parameters used to run this test. Remember, the test parameters can always be reviewed at a later date by simply clicking on the Experiment tab within a Trios results file. The second demonstration experiment will measure viscosity of a 1 Pascal second or 1000 centipoise silicone oil. The experimental parameters that we will use to measure and verify the oil viscosity are shown here. To begin the next demonstration experiment on silicone oil, go back to the experiment view and set up all the necessary parameters. Start by filling in the sample name and file location and verify the appropriate geometry. Then click on the Procedure tab and select Flow Mode and Ramp Test. Set the temperature to 25 degrees and a soak time to 3 minutes. Make sure to check the box for wait for temperature and move down to the test parameters. Choose a duration of 10 minutes with a linear stress ramp ranging from 0 to 88 pascals. Again, everything below this point can remain at their default settings. Remember to clean and dry both geometry surfaces before proceeding with this test. Confirm that the temperature has reached the set value of 25 degrees and is stable before zeroing the geometry gap. On the center of the plate, place a small portion of silicone oil. taking care not to introduce any bubbles. Set the gap to the trim gap and confirm there is enough sample to fill the gap. More oil may have to be added from the geometry edge as shown in the lower picture, and it may also help to slowly rotate the geometry while adding. When the gap is completely filled, lock the head and trim the sample using a non-absorbent tool. Then go to the geometry gap and start the experiment. Again, Trios will open the results view and display the real-time data collected. The test results from the 1 pascal second oil are shown here, plotted as viscosity and stress versus shear rate. To view the experimental parameters or the tabulated data, remember just click on the corresponding tabs at the bottom of the screen. We gave a brief introduction to Trios earlier. In this section, we will highlight a few different methods to view and present data within Trios. With the results file open, the default plot variables will be displayed. To change the selected plot variables, use the button in the top Edit ribbon. Alternatively, move the cursor over the plot area and right-click the mouse, then choose Select Variables. A Graph Variables window will pop up, allowing users to decide what variables to plot on the X and up to 4 Y-axes. Plotting in Trios allows more than one variable to be displayed on a single Y-axis, as shown here for storage and loss modulus. Any changes made can be saved as the default plot configuration. In this case, future tests of the same experimental type will be displayed with the save layout. Just click OK to exit the window. Convert the axis scaling between linear and log base 10 easily by right-clicking when the cursor is over the selected axis scale. Then just check or uncheck log and observe the axis change. For additional control over the range of data displayed, click on the scaling options found in the top ribbon under Format or in the pop-up menu as shown. We will now look into plotting data from different files on a single graph using the Overlay feature. Creating an overlay plot is a powerful data visualization tool that allows a quick comparison between different sample results. First, open all data files to be overlaid, then right-click and select New Overlay Document. A new overlay file will be created in the File Manager window, and the results view displays an empty plot. Anytime the overlay file is highlighted, it is easy to just click and drag over selected file segments to the display area. Alternatively, just highlight any open file segment and select Send to Graph from the top toolbar or using the right-click pop-up menu. The overlay plot can now be edited and saved like any other results file without compromising the original file layout. An overlay plot of 2 PDMS amplitude sweeps collected at 2 different frequencies is shown here. To apply an analysis function within Trios, open a data file, then go to the top Analysis ribbon and select the desired analysis function from the drop-down list. Highlight the data range to be analyzed and press Analyze. Please note that certain analysis models may require a specific set of variables to be displayed. If the analysis is not active, utilize the Match button to adjust the plot variables according to the selected model. Here we have performed the modulus crossover analysis on the PDMS frequency sweep data. The crossover modulus and frequency are displayed on the plot, and in this example compare well within the values specified for this lot of PDMS. The data at specific points can be stamped to the plot by right-clicking on selected point. Annotating the curve with statistical analysis is also possible. Highlight a range of data to analyze, right-click, and choose Stamp. The Annotate Curve with Statistics option will display the mean, standard deviation, relative standard deviation, and variance for the points highlighted. Here we have annotated the 1 pascal second oil data with statistics. The silicone oil we used is a Newtonian material, hence the measured viscosity is constant, and the average viscosity value closely matches the value listed on the bottle. At TA Instruments, we typically leave our instruments on all the time. However, if you would like to turn off the DHR in order to conserve air or nitrogen supply, just follow the acronym PCA. First, power off the DHR, then install the black cap or bearing lock onto the draw rod. After the bearing lock is secure, the air supply can be safely shut off. Please make sure that the power is turned off before attaching the cap, and be sure to never rotate the draw rod or remove the bearing lock unless clean, dry air is supplied to the instrument at 30 psi. Please feel free to reach out to the application support line via phone or email if you have any questions pertaining to your DHR experiments. As a reminder, the TA Instruments website has regularly scheduled training course registration, pre-recorded lecture courses, application notes, and TA Tech tips available. This concludes the DHR QuickStart e-training course, which covered the basics of DHR and TRIOS operation and demonstrated general experimental procedures required for analysis. Thank you for attending.